equals x squared minus 6 fairly easily. I didn't label these, and parabolas typically go out a bit more, but you guys get the picture. And we should be able to determine which function is on top and which function is on bottom, even though I haven't labeled them based off of the sign of the coefficient out front of the x. So since this is negative x squared, it's going to be opening downward. So it's the curve on top, and that's going to be the first function that we write that we subtract from. That's going to be this 12 minus x squared right here. And then this positive x squared is going to open up, and it's on the bottom. So we will be subtracting that positive x squared minus 6 from the other function. And so that's I'll reveal that here in a second, but we also need to determine over what interval we're going to be doing this. And so if you guys remember, to do that, we're going to figure out what the intercepts of these two functions are. To find the intercepts, we need to find when these two functions are equal, when their function values are equal. And so we're going to set the two equations equal to each other. And then we'll combine like terms and simplify. We get that x squared is equal to 9. And so our interval is -3 to 3. We're finding the area underneath the subtraction of these two functions. We're finding the area underneath 12 minus x squared minus x squared minus 6 over the interval -3 to 3. So first thing we're going to do is get this into a more workable form now that we've figured out what our integral is going to look like. So we're going to distribute this negative first. Parentheses are always important when we're doing these types of problems, always important in general. But once we've distributed this negative, we're going to go and combine like terms. And now we've gotten it to a simple form where we can easily do the reverse power rule to figure out what that antiderivative is over the interval -3 to 3. And so we get 18x minus 2x cubed over 3. And now I'm not going to spend much time going over the actual math of it, but we plug in 3 first. We plug in the top value first, always, minus, and then in parentheses, the whole function again, but with the lower value plugged in. And then simplified. Don't stress about getting this all written down because I'll send this to you guys this evening. That will be equal to 72. Any questions as to the setup of these problems or the evaluation of the integrals or antiderivatives? All right. Okay, so y equals secant squared x and y equals 8 cosine of x. So I labeled these just because I didn't want to spend much time going through how you graph these, because you guys can look up resources online as to how to graph these trig functions. But without having graphed them, it might be difficult to discern which function is which just by looking at this. And so I labeled them really quickly. And one thing to note is that we're given this interval here, which means that we don't have to do this intercept step. So long as we're taking the antiderivative with respect to x and that our delta x is going to be perpendicular to the x-axis, which it is, these little delta x's we keep referring to, then we can use this interval -π/3 to π/3 in terms of x. And we can assume, if you don't want to assume, you can double check by setting these two functions equal to each other, although that would be quite a bit of work when they've given you the answer to the intervals at least. But this is going to be our lower bound, and this is going to be our upper bound. These are our intercepts where the two functions intersect. So since I've labeled this top function here y1, it's going to be, oh wait, no. So in last recitation, I had to make this correction as well. So this should, what did I have that as y2? That should be y1, and this should be y2. Okay, so 8 cosine of x is our function that's on top, and secant squared of x is on bottom, so we're subtracting that from 8 cosine of x, and over the interval that we're already given, -π/3 to π/3. Now, the next step that I'm going to do, I'm going to take a step back and address number 13 really quickly. Since both of these functions are symmetrical and they have a symmetrical interval, and an interval that's easily broken up in half, you don't have to do -π/3 to π/3 or -3 to 3. What I could have done for this problem was I could have found the area underneath 0 to 3 and then multiplied it by 2, because this area on the right is going to be equal to the area on the left. So I could have evaluated this integral over the range 0 to 3 and then multiplied with a 2 out front, and I would have gotten the exact same answer. Same deal down here. That's what we're going to do. So I'm multiplying by 2 and I'm assessing the integral over half the interval. And I'm able to do this because the function is symmetric about the y-axis and my interval is also symmetrical. And from here, we can find our antiderivative. So first addressing the 8 cosine of x, what function gives me the derivative cosine of x? The derivative of sine is cosine. And so the derivative of 8 sine x is going to be 8 cosine of x. Secant squared, hopefully we have that antiderivative memorized. We know that the derivative of tangent is secant squared. And so we get 2, we don't forget about this 2 times 8 sine x minus tangent x over the interval 0 to pi over 3. And from here, we just plug and chug. And again, don't worry about getting this specifics down here. I'll send it out to you this evening. But one thing I do want to point out about this, just bear in mind that tangent of x is going to be sine over cosine. We'll do a problem later on that's inverse tangent. That's going to be cosine over sine. So you got to evaluate those separately and then divide. And that's what this little fraction of fractions is here. Any questions on this one specifically? We're going to do one more area problem before we move on to chapter 6 review. Okay. All right, so y equals x cubed and y equals x. Hopefully we can visualize both of these functions fairly easily in our minds. So x cubed, our cubic function, we know that that looks like this squiggle here, and then a linear function, we're all familiar with that. So we're going to have to find these intercepts, and if off the top of your head it doesn't click that x is going to be equal to positive and negative 1, then you can set these two equal and actually go about the math and subtract this x over, set it equal to 0, factor out, and find out what those values are if this doesn't click for you. But those are going to be, this is going to be our negative 1 is going to be our lower bound, positive 1 is going to be our upper bound. In a typical scenario, what's atypical about this is that we change from having the cubic function on top and a linear function on bottom to the left of the y-axis, so over the interval negative 1 to 0, to having the linear function on top and the cubic function on bottom over the interval 0 to 1. And so we have to reflect that change in our integral statements. And so it's going to have to shake out to be two separate statements because we're going to be subtracting the cubic function or the linear function from the cubic over the interval negative 1 to 0 and the linear function or the cubic function from the linear over the interval 0 to 1. So this is also a symmetrical function. It's not symmetric about the x-axis, but it is symmetric about the y-axis. And that's what we need in order to do this, break the interval up in half and then multiply the area by 2 sort of deal, this shortcut. So we can do that by just getting rid of one of these and multiplying by 2. So the important things so far, so we've graphed the function, we figured out the intercepts. Hopefully that was review. Maybe we haven't really talked too much about functions that are symmetric about the y-axis, but not about the x-axis. And the important thing to note is that you have to pay attention to which function should be subtracted from which, and that might cause you to break up your intervals. Then going one step further, this would be perfectly acceptable. You could evaluate both of these separately and not even do this trick step here. But going off of that, we also know that these two areas, because the function is symmetric about the y-axis, that these two areas are going to be equal. And so we can just evaluate one of these. I'm going to choose the easier one. In my mind, positive equates to easier, and multiply that area that we find by 2. And so the antiderivative is going to be x squared over 2 minus x to the 4th over 4 over the interval 0 to 1, all multiplied by 2. And that is going to be equal to 1/2 once you crunch out the algebra. Any questions on this one? Okay, so I had mentioned earlier that differentiation will come up on this exam. I don't know for certain. I have my meeting with Dr. Zlecki tomorrow morning, so I don't know exactly what's on your exam. But I wouldn't expect there to be, and like I said, I don't know for certain, I wouldn't expect there to be problems where Dr. Zlecki asks you explicitly to find or to differentiate, to find a derivative. That being said, we didn't really do much with Euler's function or with the natural log function when we were doing our differentiation, when we had differentiation on our last couple of exams. And so there is a chance that he might put a little emphasis on it with integrals, or maybe that he'd throw in a couple of differentiation problems. That being said, there's really not a whole lot to memorize in terms of what's new for the natural log and Euler's functions. And we'll see that it's really just applications of the power rule, product rule, quotient rule, chain rule, whatever we have to use. And then one more step that you have to memorize. So the derivative for the natural log or the derivative for Euler's number, which are both pretty simple. So starting with number 21, we've got two functions being multiplied. So we're going to have to apply the product rule. We're going to do the derivative of the first times the second. So 2t natural log of t plus the first t squared times the derivative of the second, which is just 1 over t. So that's all you have to memorize for a natural log function. Everything that we've done so far, everything in this step here is familiar, except for maybe this 1 over 2 being the derivative of the natural log of t, because we didn't really do much with that earlier in the semester. But other than that, it's the same skills that you've been using. It's just one more thing to memorize. And Euler's function is simple as well. This is just the simplified version. So now let's take a look at an example of Euler's function. So Euler's function, when you take the derivative of it, the derivative of e to the x is e to the x. Technically, whenever you're taking the derivative of Euler's function, it's itself times the derivative of whatever is up here. So if I ask you to take the derivative of e to the x, then that derivative would be itself times the derivative of whatever is up top. So it's still just e to the x. But since this is not just a simple x, a simple theta, we're going to have to figure out what that derivative is and multiply it by it. So the first term that we're going to have is e to the tangent of 2 theta. Now we're going to have to multiply by the derivative of tangent 2 theta. So there are going to be two aspects to that derivative. First is going to be the trig aspect. So we know that the derivative of tangent is secant squared. So we're going to multiply by secant squared 2 theta, keeping everything on the inside the same. And then we'll multiply by the derivative of the inside, which is going to be 2. So the Euler's function is, when you take the derivative, it is itself multiplied by the derivative of whatever is up raised to the power. And in this case, we have another chain, another link in the chain for the chain rule, because what's inside the parentheses tangent of theta also has a derivative of 2. Any questions on natural log derivatives or Euler's function derivatives?
Do we have to simplify?
What I've shown you so far, that's acceptable.
Okay.
There's no real way to simplify this further, unless you were to like rearrange the terms, but I wouldn't expect anyone to do that. All right. Number 27. So we're going to have to apply the product rule here. We've got x multiplied by tangent inverse of 4x. And then within the product rule, we're going to have to apply the chain rule twice. So we're going to have to take the derivative starting with this power rule aspect. So if you guys recall, you can visualize this -1 or to the negative first power. If it's in the middle of the trig phrase, you can also visualize there being parentheses around tangent of 4x and it being put to the negative first power. If when you do your chain rule, you think about working your way from the outside in, because this -1 is being applied to the entire deal. And so it's our outermost aspect of the function. And so, well, let's just dive into this first. We'll have the derivative of the first times the second plus, so now it's going to be the first x times the derivative of the second. First aspect we're going to address is this power rule aspect. So we'll drop the -1 and it'll be tangent. I did this in first recitation too. So I got ahead of myself. We're not going to be doing this. Tangent inverse has its own derivative that we memorize. And I went off the rails explaining this the way that I thought it would have been in first recitation. It just didn't click for me again for this recitation. But like I said, product rule. But the only thing that's new about this is that we're memorizing that the derivative formula for tangent inverse of something is 1 over 1 plus whatever the constituent is squared. And just like this morning when I saw this, it clicked, it makes perfect sense. But tangent, just like the natural log and the Euler's function, tangent inverse is just another new derivative that we memorize and we apply with our other differentiation techniques that we have already learned. So like I said, the derivative formula for tangent inverse is 1 over 1 plus whatever's inside the parentheses squared. All right, so this one, again, we're going to be using Euler's function, and it's going to be an example of the quotient rule. So first thing that I do is I recognize that e is to the x to the negative first power, because I'm going to need to use the power rule at some point. So I've done a fractional power manipulation. This is 1 over x, which is x inverse. And so diving in, we get the derivative of the first. So we drop that -1. and then derivative of the first times the second minus the first, that should be an x, times the derivative of the second over the second squared. And like I mentioned before, I wouldn't expect you guys to simplify this much more than this. And that's all Dr. Zlicki asked me to bring up as far as differentiation goes. The rest of our recitation will be going over four or five integration problems. And any questions on differentiation? Okay. All right, so 4 problems. Yep, the first 2 are going to be a couple of problems where we mess around with changing the boundaries. And I'll get into that a bit more in a second. But then the second 2 are just going to be some plus C ones. Oh, I think they're pretty much all use substitution examples. The only difference being this one is a plus C situation, and then these are we're going to evaluate for their actual value. And we're also going to talk about changing the upper and lower bounds. So first thing when addressing these composite integration problems, you see all this business, you're probably going to have to use substitution in order to figure this out. So when we're doing use substitution, what we look for is the quote unquote most complicated aspect of the function. And by that, I mean, well, in this case, it would be e to the negative 2y squared. And then we think, okay, when we take the derivative, if this is what's left over from the original function, is there something else that's a part of the integrand, that's a part of what's between the integral and the dy, the integrand? Is there something else that's a part of it that could be the product of taking the derivative? And so we know that if we take the derivative of Euler's function, it's going to be itself times the derivative of whatever is raised to the power. So the derivative of what's up here is going to be negative 4y. So all we're missing is that negative 4, and we can easily account for that with a factor that we can put in later in our u substitution, but we've got that y, and so we can say that it's going to be e to the u is going to be equal to negative 2y squared, and then du, this is going to be our aspect of the derivative. So as we take du, we get negative 4y dy. We don't have that 4 yet. So what are we going to do? We're going to do a manipulation so that negative 1/4 du, when we plug that in for y dy, that negative 1/4 will cancel out with the 4 when we take the derivative of what's raised to the power in Euler's function. So we've got all that down. This is normal u substitution, but the only thing that's different that we're going to talk about here is we change these boundaries. Now, when I get to this step over here, I'll make mention of how you don't necessarily always have to do this. But first, let's just talk about what we're doing here. So we're doing the plug-in step. U is equal to negative 2y squared. So we plug that in here and it's e to the u. We also have y dy equal to negative 1/4 du. So we plug all that in. And now addressing these boundaries, what we're going to be doing here is sort of cutting a step out in the sense that if we change these boundaries from being in terms of x to being in terms of u, we can plug in directly to u when we take the antiderivative. So let me show this one step here. So this would be the antiderivative, e to the u over 4, negative e to the u over 4. If we take the derivative of this, we're going to get this. So now, ordinarily, we would plug in u here, and we would then evaluate using the interval 0 to 1. We'd plug in and we subtract to the function e, or negative e to the negative 2y squared over 4. But that would work if we do that when we have our bounds in terms of x. We're going to do it with our bounds in terms of u. And so what we're doing to do that is, so this should be y. So when y is equal to 0, so our lower bound was 0, y was equal to 0. What is u? If we wanted in terms of u, what would u be equal to? So we plug in 0 for y and we get that u is equal to 0. Same deal down, or for the upper bound. If we want to figure out what the upper bound is, if y is actually equal to 1, then what is u? It is negative 2. So now we are evaluating the same integral. We'll get the same answer. And instead of doing it over x equal to 0 to x equal to 1 with, or not x, excuse me, y equal to 0 to y equal to 1, and plugging in this negative 2y squared here, we're going to leave the u and we're going to plug in our values according to u. So u equal to 0 and u equal to negative 2. And so when we do the math on that, it shakes out to be equal to this. But that is still equal to evaluating this integral, having plugged in u where we are used to plugging it in, and then evaluating it over the same interval. Those are two equivalent statements. Does anyone have any questions on this one? We'll do another example, number 95. Okay. All right, so over the interval 0 to 1, we get e to the x over 1 plus e to the 2x. So first, whatever our u is, it's going to have to do with Euler's function, right? So we've got u equal to e to the x, and we'll see why in a second. So if we take du, we also get e to the x. So plugging in, we'll come back to the boundaries here in a second. This looks, if we can recognize this format here as being similar to the derivative of tangent, I believe it's tangent, or maybe tangent inverse, excuse me, then we can recognize that u is going to be equal to e to the x, and then u squared would be e to the 2x, and then the derivative of e to the x would be popped up on top. And so that's how we're breaking down this. That's how I'm looking at this problem and trying to figure out what should be u and what shouldn't be. So, and what antiderivative we're going to have, because you got to kind of take into account it all when you're setting up these problems, and they look, especially if you're doing these tangent inverse problems, because it gets a little messy with these extra terms. But after having identified that u is equal to e to the x, du is equal to e to the x dx, then this starts to look more like our formula for tangent inverse. And we'll get to these bounds in a second. It's the same method as before, but when we take that antiderivative, we get that tangent inverse of u over 0 to e is equal to this original statement, and that is true. So now let's address the bounds. So when x was equal to 0, what would u be equal to? U is equal to 1, because e to the 0th, anything to the 0th is equal to 1. So now the upper bound, when x was equal to, or if x is equal to 1, what is u equal to? U is equal to e. So now we're evaluating, this should be over 1, over the interval 1 to e. And plugging in those values, we get tangent inverse of e minus pi over 4. So I'll remind you guys that tangent inverse of 1 in this case would have been cosine of 1 over sine of 1. All right. Moving on to, so that's our last example with the switcheroo with the boundaries. Anybody have any questions before we move on to the plus C examples? All righty. So number 97, hopefully it's not too difficult to look at this problem and sort of pick up on what is the original function and what is the derivative, or what is the product of taking the derivative. So e to anything is, when you take the derivative of that, is going to be itself times the derivative of whatever that anything is up top. So the derivative of e to the square root of x would be e to the square root of x multiplied by x to the negative 1/2. So that's the square root of x down in the denominator. So it's going to be pretty straightforward. We say that u is equal to the square root of x, or x to the 1/2 power. And then when we take du, we get this 1/2 x to the negative 1/2 dx. So the 1/2 is the one thing that we don't have, that isn't accounted for. And so when we manipulate and find what dx over square root of x is, we get that factor of 2 that's going to cancel when we take that derivative. So again, I'm not just setting it equal to dx in this case, I'm setting it equal to dx over the square root of x, because I'm substituting in for dx and square root of x. So then it looks like this. We get 2e to the u du. We don't deal with the square root of x, because at this point, that's a part of the derivative. It's embedded in our dx. It's embedded in our du. Du is equal to 1/2 dx over the square root of x. But we keep that 2 in order to cancel for when we take the derivative. And then taking the antiderivative, we get 2e to the u again. So that 2 maintains because it's a constant, and the derivative of e to the u is just e to the u plus c. And now we plug in that square root of x. And if you're unsure, you can always double check. But when you take the derivative of this, the plus c goes away, and so does the 2 when we drop the 1/2 for the square root of x. Any questions on this one? We're flying through the material much faster than first recitation. So if you have any questions, please say so. All right, last problem. So looking at this problem, what is the most complicated aspect of the function? It's the denominator, and the numerator looks like it could be the part of the derivative of the denominator if the denominator were the original function. So let's say that u is equal to x squared plus 2x. So if we take du, we get 2x plus 2, which when we factor out of 2, or 2x plus 2 dx, excuse me, which when we factor out of 2 is going to be equal to this little bit up here in the numerator. So we now have that 2 times x plus 1 dx is equal to du. And so then what is x plus 1 dx equal to? It's equal to 1/2 du. So we're substituting in for x plus 1 dx, leaving the original function. Well, not leaving it. We're going to be substituting in for u. And then we plug in our 1/2 du. So 1/2 du just goes right up top. You can visualize this dx as being up top as well because it's being multiplied by the fraction. So that's this 1/2 du over u. So what function gives 1 over u as its derivative? The natural log. And when we do, when we take the antiderivative of something that we know to have the natural log as its antiderivative, we use these absolute value symbols. The 1/2 is maintained because again, once we plug in that u, it'll be a part of it'll cancel out with the derivative such that we get the correct integrand and everything checks out. But then we